Hello, everyone, and thank you for joining this seminar. My name is Vladimir Marchenko. I'm a product manager at Arm, based in Munich in Germany, where we have a team dedicated to software development solutions for Cortex-M microcontrollers. It's the simple processors that based on Arm architecture, and we also have some automotive groups there. And know-how is our valued partner in Nordics that helps us serve the development teams and the engineers that use our tools, KLMDK, Ulink Pro, for developing software, embedded software on these Cortex-M devices. In today's presentation, I will talk about the fault detection capabilities of Cortex-M architecture and how it can be used in safety systems with mixed criticality. The agenda is pretty straightforward, a brief introduction, then I will explain a bit on the use of ARM-based microcontrollers in safety systems with a look into the fault exceptions. After that, the software development on such microcontrollers with different safety integrity levels, so-called mixed critical systems. I will introduce our approach to that with ARM runtime system for functional safety, and how the error and fault analysis and recovery flow can look like. I have prepared a small demo as well. And after that, we'll have a summary and open to your questions. So from the definition of safety critical systems, as we know it, is systems where failures or malfunctions may cause health and environmental damages. Some people want to put financial damages in there as well, but it's not the main focus, at least. It's clear that the failures and faults of such systems is actually the largest part of functional safety. Really, and that's why there is multiple methodologies focused on those faults. The FMEA for failure modes, effects analysis, the fault tree analysis, HARA for hazard and risk assessment, and many others depending on your industry and the needs where safety managers are greatly involved in analyzing the systems. And there are generally two types of faults that kind of specifically in the electronic systems that are considered. One is the systematic capability or systematic faults covered by the systematic capability of your system. These are hardware errata, software bugs, some incorrect specifications or incomplete requirements. And the idea in the safety, in the current safety concepts is that this is managed through design process. So this is polished out during the development and doesn't exist in the final system. And there are some other faults that can happen, random faults in hardware that basically you cannot avoid. Something just not working suddenly as it's supposed to. It can be a permanent fault, or it can be a very short-lived transient fault. And this sort of faults need to be managed by your diagnostic capabilities, the capability to detect them and kind of mitigate in that sense, or at least detect is already a good thing to have. But in this session, what I will try to discuss is really how we can use these diagnostic capabilities and how we can use them to actually resolve some systematic faults that specifically the software bugs that you cannot avoid in the system. And in many cases, in the mixed criticality cases, you actually don't want to spend the effort on covering providing the systematic capability for your complete system. So first, let's look into the ARM microcontrollers in safety systems. So as you know, ARM is probably know ARM is a IP company. We create architectures for processors or other semiconductor blocks that we license to the chip vendors, and then they create really or manufacture the devices and sell to the end to the OEM or developers to build the systems. So, but even in that flow, we also need to take safety into account during the development of our architectures, and in two ways, exactly to cover those capabilities that I've just mentioned. The diagnostic capability, basically to address those random faults that can happen. Some of those we provide as part of our architectures. Some we enable other or custom or vendor-specific implementations as well. And the other aspect is the systematic capability, so that we demonstrate that our processor is designed with following by the functional safety standards, and there are evidences how it's validated, and all the development processes are compliant to corresponding safety standards. So this is usually the packages that the chip vendors get, and they are not public, and developers for safety systems don't see them directly. So if you look at the diagnostic capabilities or general maybe safety-related features in the microcontrollers, I didn't want to go too much into details, but there is a full list of those. We have basic privileged, non-privileged execution rights for the code. There are fault exceptions that we will look a bit closer on the next in the next part. There is a memory protection unit to isolate executions or access to certain memory and peripherals. There is a CRC protection and error code corrections for the memories. There are lockstep capabilities, watchdogs, and so on. And those, but what is important to understand is that these are blocks or capabilities that are optional to implement for the device vendors. So some privileged, non-privileged execution fault exceptions are pretty much mandatory, but then MPU and all the rest is optional. So it's not every ARM microcontroller would have it, and even maybe in some cases most would have. MPU is pretty common to find in many Cortex-M4, M7 devices. But there are always exceptions, and it's important to check with the datasheet and documentation of the device to really see what's there. There are also custom implementations of these functionalities. So it might be ECC, but it's not ARM ECC. It's someone's. Well, it's a custom one, and then it's a custom MPU that a vendor might have, and then it would be controlled differently, and you would need a different software for that. So what usually the chip vendors provide for such safety projects with their microcontroller hardware? They would have a so-called MCU safety package that includes the FMEA that lists the failure modes and how they can be mitigated with computed failure rates. Probably some parts of that is taken from our documentation or is supported by our safety documentation, but it is done then in the end for the specific device. Then there is a safety manual with the safety requirements, how to achieve a certain safety level. Often there is a self-test library, the utility that runs on the device to diagnose permanent faults in the hardware. And there are many such devices on the market. This is just a list from the most common microcontroller vendors in alphabetical order. We don't give any preference. We love all of them. The Infineon has, of course, famous for the automotive families, but they also have the Cortex-M based microcontrollers for industrial market. Microchip has good coverage for with the SM family. NXP has an automotive line as a S32K, and I think it's extended 32G. And others, but there is also industrial support, or there is household appliances as well. Renesas and STMicro. And what we see that very often there is, of course, in general in safety market for these components, if they start successful in one area, specifically in the automotive, then it's easy to extend and certify it for industrial or medical applications as well, as the concepts are very similar, and it's mostly just a matter of some feature set reduction. In automotive, it's more demanding, but it would work in many industrial spaces, of course, as well. It's not an ASIC device. It's not an application-specific device in the end. It's a sort of general compute device. And there are many others from smaller vendors that you may know or work with, and many more to come. So definitely a very vibrant space for us and our partners. Now coming back to these faults that can exist in your systems. If we look at the Cortex-M fault exceptions, and these are the interrupts basically, or interrupt level executions that preempt the program flow to indicate that there is something went wrong in the system. And of course, the most so this is just a brief overview to list as a reference. There is a lot of materials that I will mention as well. The hard fault, most famous example, and the one most people see, because it's a must-have, and you cannot avoid it. The others you can configure to have a specific separate handler, but if it's not configured, you would end up with a hard fault. The mem manage fault for the instruction access or incorrect data access, as well as the protection of the MPU regions. There is a bus fault, usage fault. It's with stack overflows, division by zero, unaligned accesses, and so on. And on the latest architecture, Arm v8M, with the trust zone support for handling the secure and non-secure code. There is also additional secure fault that indicates that there was a violation of these security settings as well. And it exists since a long time, since the Cortex-M, I think, since the Cortex-M is there, with some improvements, of course, in more advanced cores, and it's a well-covered topic. In general, there are application notes from us or the technical references, and there is also third-party coverage from in the blogs, like an interrupt blog is a very good place for embedded software development guidance. And there are also different development environments which support you in debugging or catching these sort of faults. But there is a big but, as you can see here at the end. There is a very good theoretical coverage for this topic, but it's much less, I would say, coverage in the software, in the examples and utilities to deal with that. Even if IDEs do support it, but they require mostly debug connections for the analysis, which is sometimes not practical, or if it's a CI system, or just you don't want to bring an interruption through the debug channels. And generally, the implementation of this fault handlers is pretty tricky, right? Even if you're a processor expert to some extent and understood this theory, you need to, in many cases, you need to use the assembler to properly handle the stack and registers, and this is not something that people do on a volunteer basis, right? You need to find an expert often and someone willing to deal with that as well. So especially younger generations wouldn't go for that easily. So we understand the problem and the challenge. And we introduce also some additional software and utilities to deal with that. Our CMSIS ecosystem, so we use our CMSIS ecosystem. This is the Cortex-M software interface standard, a set of different API definitions, software components that simplify software development on the Cortex-M devices specifically, and they cover everything from different debug, DSP, general drivers, RTOS, and so on. And we have a component called CMSIS-View that generally meant to use to annotate your code and analyze the execution flow, basically, and see how it works. And we have added to that component a fault analysis capability that works as shown here. I'll explain. We first, when there is a fault exception that happened, we provide a function that can be called Arm fault safe that copies the fault relevant data into a specific structure in RAM. And this RAM is uninitialized. That means that after reset, it will be kept, so it doesn't get erased after a reset. And the reason for that is out of the fault exception, you're very limited to do something, right? So it means your system doesn't work. You cannot store this data into the file system or print it into UART. The system is stuck. And if you even try to do that, very likely then your configurations, your stacks and registers will change, right? So you will not get the accurate information by the time you put it out. So we save it in that area, and then you exit this exception. Typically, yeah, of course, you could put an infinite loop there and wait until someone comes, maybe tries to. Yes, sorry.
I was just wondering if any of the slides that are presented today will be shared afterwards, or should we make our own?
They will. Yeah. Even the video, so you can walk out if you want to. Yeah, so don't worry. I understand lots of information, many links, but you'll get it to follow up later as well. So you could that fault, of course, if you do it local debug, maybe often there is an infinite loop, and or you put a breakpoint and try to analyze it on the spot. But as mentioned, in the CI systems, it's not practical very often, or you cannot do these sort of hot debug connections, and then we would restart the system to recover. And after restart, there is another check that verifies, yeah, was it caused by a fault or not? And if it is, we can just go and print this data. It's all in RAM, and you could put additional information if you need to. And then either we use a standard output into UART or a file system that can be logged and analyzed, or we also have a graphical utility in our debugger, and well, we'll have it in a bit nicer way in the VS Code as an extension as well, and where you see a graphical representation with that data. I'll show a demo a bit later on that. It's an open source component. Anyone can use it. It doesn't require. It's not bound to any specific compiler or debugger. It actually, yeah, would work. It does not depend on other components. As I said, lots of assembler code. So I don't understand it, but I use it. So, so that's a great tool to analyze your faults and basically get rid of that sort of bugs in the system, right? So that's then easy task to develop software. Yeah, just kidding on that. If we look in the software development for safety projects, then what was shown before is famous V model, where we need to, for the safety software, we need to be very rigorous on the requirements, on the specifications, and validation of all those requirements, and with a lot of reports, reviews, and so on. Right, so okay, CMSIS-View and our fault exceptions help you, but okay, now you need also to go through this model, and then we consider you are done. And that was the approach in safety for, and it is for many cases. It works okay, but as also mentioned by Rizwan, in modern applications it becomes very tricky to do. Right, because if you have enthusiastic engineers, they like to use code from other places as well, and then the modern embedded system would look like this. You have an Arm Cortex-M device underneath. There would be a standard C library coming from the toolchain. There is a HAL with some peripheral drivers, probably coming from a chip vendor. There is an RTOS to manage the middleware, and on the middleware, well, you could have an infinite number of those blocks. Typically, there are several different vendors that would come in, or open source components as well, and there is a software test library just running and testing the hardware capabilities. So many different components come in play now, because you also want to use that. Our devices become more powerful. There is more and more compute you could do. There are more and more features that chip vendors add on that, connectivity, AI, graphics, controls, and so on. And well, it is, right, so there are cases of Cortex-M running 1 gigahertz, and you can do a lot of stuff right there, and the memory is added as well. And in safety, what it means is to make it safety compliant, you need to do this V model across all of these components. Not practical, of course. There are often some safety variants of those components, And ARM provides that as well, right? So we have an ARM FuSA RTS that I will explain on the next slides with the C library, RTOS, parts of HAL. There are some middleware vendors that have safety variants, but for one, it may not be suitable for specific applications, and then it's very limited in coverage, right? So there are many software that doesn't have any safety variant. So the approach really to how to solve that problematic is to partition your system into safety critical and well, less safety critical functionality, and and basically protect your safety functionality from possible interference from your non-safety functionality. And this could be done often, or was done previously with the two different devices. But again, as I mentioned, it's possible, right? So you could do, but you still need to implement the communication between those devices and keep it kind of protected. Additionally, when you add another device, your BOM increases and your logistic complicates, right? So with chip shortages, if that chip one chip will not become available, you're blocked for the complete device. So it's great to have it on one device, and it's generally possible. You could. It is possible, right? And we do it with the FuSA runtime system that I explained in more details, but there are other approaches that are possible on our Cortex-M architecture. With that, you could basically reduce the effort for validation of your non-critical functionality in the system, reuse existing software that was done in non-safety projects, or maybe coming from other third parties or open source, and create differentiated product that has advanced features really. The prerequisites for that, or even the requirements actually to achieve that, are listed here. We need to have a spatial isolation, meaning that there is a protection from protection to the memory and let's say the functionality across these blocks. That you cannot violate the memory for critical function that impacts operation of critical functions. Then there is a temporal isolation, meaning that your safety critical functionality gets the required processing time from the CPU, right? And it's not locked somewhere accidentally in the non-critical side. And there is an option to recover the system in controlled way. If you have these failures, any failures, they get detected, and you have an option to decide how to transition to either a fail-safe state or try to recover your system. I've mentioned it a few times, the ARM runtime system for functional safety, or shortly FuSA RTS. It's our set of software components that are certified for use in safety critical applications, and there is certified by TÜV Süd for this, for all common safety standards. And the way we came to that is we have, as I mentioned, the CMSIS components that are open source and very popular on the general market by the microcontrollers. But we wanted to look into that and analyze in more details how it's suitable for safety and extend the functionality. That was a great exercise for our team, and we created the safety variant basically for that software. And our goal is actually we also contribute back to the CMSIS many features, bug fixes, and etc. They are not staying within this FuSA RTS only environment. They contributed back to the open source variant as well. So it's pretty much identical code base. But this is, of course, certified. There is a safety manual and evidences that you would need safety system. So the components, the software blocks in this package are shown here in blue boxes. We have a certified C library that is a standard C library that is, although limited in the functions, because we had to it is limited in the set of functions a bit, and it's a bit simplified implementations to ensure that there is a good code coverage and the implementation is safe. We had to a bit tweak the implementations and make them simpler, so they are not one-to-one to our standard C library in that sense. CMSIS core is an abstraction layer to generic CPU functionality. That we have, we implement the ARM part, and we also have a standard defining how the chip vendors can do their part. But of course, the chip specific or vendor specific implementations are out of scope for our testing. We cannot cover those. There is an RTOS with all the features you would expect from an RTOS, really. And the event recorder is this component that I mentioned as in CMSIS-View that you could optionally use to analyze program flow or for this fault analysis. We currently support, we have it commercially available for Cortex-M0, M0 Plus, M3, M4, M7. And we are working on getting the same for Cortex, certifying is basically certification work because we have it already in the open source implementation, but to validate and certify, we need now a bit more, a bit of time. But it's coming next, maybe early this year or early next year, the variant for our latest Cortex-M course as well. So if we look back at these process isolation features that are needed to implement mixed criticality systems, the spatial isolation is one of them, and here's how it is implemented in the FuSA RTS. The Cortex-M devices have two operational modes: handler mode with privileged global access, basically, and thread mode. Or user mode with a non-privileged, generally not non-privileged access, but you could configure it in some cases where it is needed. And we would, here we need to split the functionality or application functionality into different, logical or functional blocks, right, and group them where they need to access or do similar functionality or similar safety level functionality and use the resources. And so we use the memory protection unit for that, and it's a mandatory component to have on the device. As I mentioned, it's optional, and some vendors do not do it in their implementations, but it must be present actually to achieve this spatial isolation. So we could take our user threads and assign them an MPU regions that they are allowed to access, basically, right? And we can do this for many threads, or it can be just two if it's critical, non-critical, what is most common. But there is no real limitation on how many you could have. It just complicates maybe things a bit more. And as soon as your code in the thread tries to access some other region it's not configured for, then you would get a mem fault, and you need to decide what to do next. That we'll discuss on the next slides, but you get it. You get your protection actually in place. There is a caveat to that, of course. As you can see, there is an interrupt handlers. They operate in handler mode with privileged access, meaning that you could do everything from an interrupt. Well, you can access everything from an interrupt. And so even if your software if you have software components that are considered as non-safety critical, the interrupt handlers that they implement, you still need to understand and analyze really that there is no potential issue in there, and do of course in the interrupt as little as possible, and transfer the execution back to the threads. But it's much less code usually, and manageable as well, right? You can have shared resources. Of course, there is a need to communicate between the threads. It can be done through the kernel resources, but often you need some additional memory that is shared, and that can be set up as well. Yeah, so this is the approach with MPU protected zones. It's required, but it's not sufficient. What is the problem of well, what was missing really in the RTOS, and it is missing in many other RTOSs, is that when we try to when we operate with the RTOS objects, such as threads themselves, timers, semaphores, etc., it's not done by the direct memory access. It's done through some ID of those objects and an API call to the RTOS kernel. And that means we cannot really, they're not getting protected through the MPU. We call in, anyone could call that API and accidentally or on purpose change that ID or pass that ID, and it will execute, the RTOS will execute that command, and it can be changing of priority thread or doing something with the timer. And of course, if it's an object that is critical for your safety code, it's not a desired operation. So we needed to protect against that. And this where we introduced the safety classes. And the safety classes, they can be, you can use them together with the protected zones and just use the same numbers for simplicity, but it can be also, it's an independent mechanism as well. So how it works is that every RTOS object, when it is created, you can assign a safety class to that. And if you don't do that, it will inherit the class of a thread where it is created. And then when an API is called to an RTOS to do some manipulation with this object, there is a check that this API is called by a thread with at least the same or higher safety class. So meaning that your low safety class threads, if they try to call APIs with something modifying or manipulating objects that high safety class threads use, then it will not work. It will return an error that this is not permitted execution. And with that, we basically provide the special isolation for the memories or memory mapped peripherals on that MPU allows, but also on the RTOS side of the RTOS objects. On the temporal isolation, what we added is so-called thread watchdogs to monitor the timing execution of the threads. And for each thread, you can set a thread, a local watchdog timer that needs to be serviced as configured. And if it's not being reset, then there will be a watchdog alarm notification that again allows you to understand that this situation happened and try to handle it. For example, if we have a thread A1 with a low safety class and we feed the thread watchdog, all works fine, but that at some point there is a timeout, and we can, in the handler, we see that this thread was not serviced at time, and then we can decide, okay, this is a low safety operation, something is going wrong, let's just suspend it, and then that we don't want to risk any problems on our high safety operation. This can happen also on the high safety thread, right? So the high safety thread can operate correctly, and watchdog is serviced, but at some point it might not get it time, and then there will be a watchdog alarm. So now we have a high safety threat that is not serviced. This is a very dangerous situation, but one assumption can be that this is because something went wrong in our non-safety operation, and then we can say, yes, so suspend everything that is not safety critical, and let's see if it helps. Right. So this is not a last resort, of course, check. It needs to allow some extra time. That if it doesn't get serviced again, then there is this is then a really situation to avoid with all those V models and stuff. But it still can happen, and then we can transition to a fail-safe state and basically do stuff differently. And here's a very kind of straightforward error and fault flow analysis that we allow to implement. Right? We provide those mechanisms so that they're available for use, but so that you could do the most difficult part. So unfortunately, it's not the vice versa, that we do the most difficult part and you don't need to do much. We remove those general common parts, but the most critical and difficult things is actually application and system specific, and that's what then engineers need to handle. In this case, when there is an error notification or fault exception, first step is really to analyze it. Yeah, what really happened, and that's where the most effort would come to, and where we provide some mechanism, but the decision what to do next is again on the application side, and then we provide some APIs and mechanisms to achieve what you might want, but the hard decisions are really for the application to do. In this case, so we analyze the error and fault. If it's a critical, really critical thing, then we need to proceed to a fail-safe state, right? And we cannot do our default continuous safe operation anymore. Something is really bad. We need to either shut down, or if we cannot shut down, then in a traffic light we start blinking yellow until there is a service coming and checking what's wrong. But if it's a non-critical fault, then we have a mechanisms to suspend non-critical threats or non-critical operation. In that sense, we proceed to a degraded system operation. We don't have all coverage. If it's, for example, a network stack or a CAN stack for communication, we may suspend that, but we still would keep our safety operation running. Right? So one of examples is if it's an insulin pumping device and it has an insulin control pump, and it may also have a Bluetooth stack to communicate with smartphone for some information logging and so on. And if your Bluetooth stack doesn't work, you probably still want to get some insulin until it is recovered, right? Until you come to a service. But if a pump control mechanism doesn't work, then you just stop pumping to avoid that it's too much or incorrect amount is done. So there is a degraded system operation where your well, default safety operation is continued, but non-safety is stalled, and we can try to restart it as well if there is a mechanism for restarting the software without impacting the safety operation. This table shows a list of errors or faults that you could have, examples. It's not, of course, all of them, but in the FuSA RTS or RTOS systems, you would have something like that, and some decisions whether it's critical or non-critical. Threat watchdogs, I've explained on the previous slide. The RTOS provides also errors for thread stack overflows, incorrect SVC calls, time queue overflows, and then you could decide is it triggered by a critical thread or not, and handle it accordingly. There are default exceptions that we've seen in the beginning, hard fault manage, and bus fault and others. Again, allow you to trace back what has caused. Well, in most cases, you can trace back to the thread that caused them, and then decide again if this was done by the critical or non-critical thread. In some cases, you can have an error coming from the interrupt or an unknown origin, and then, of course, it's mostly critical situation that. There can be exceptions or options to analyze it better, but in most cases, it's a critical situation. And there are, of course, other types of errors you could see coming from the startup codes, from STL diagnostic, and so on. But then it's very application and system specific to decide on how to proceed with that. So let me, before we go to summary, let me show you a demo. If we come back to the screen. That's strange. I'll try to reattach it. Or maybe it's configured just to show PowerPoint. I don't know. Got scary from my code. No, it's back. So we have an example called fault handling that is pretty simple. We create two user threads. One is for normal operation. The other one is safe operation that run at the same time. And they are configured, following all those concepts with the watchdog timers, with the MPU protection, and so on. And we have a capability to inject a fault from different types of faults in there. There is apparently those faults that we've seen is just tip of the iceberg. Actually, for all of them, there is many different subvariants and reasons that you could analyze. And so we have, I think we even don't do all of them here, but we have 41 variant of a fault that you can inject, and then we implement this. Let me show some code for that. So the faults the fault handlers are kind of combined into one, and this is a fault handler ASM, where we call actually the fault safe function to store that fault information, and then after that there is a fault exit operation with lots of assembler code that I gave up on trying to understand, but engineers say it works, and they find ways to optimize it now and then. So with this assembler code is we basically handle all the registers and stack to ensure that we can continue execution of the C functions to analyze the faults then, right? So then it comes to the code that I can at least read without breaking my tongue. But it's a standard C code where we can analyze the registers and see what sort of fault it was. Did it come from thread or interrupt, or where from? And then we can decide basically what to do. An example, so it runs currently on the Cortex-M4 device, and I will use a debugger just to have a graphical representation, but it's in a similar way we could see it from the, as I explained, with the standard output after reset. And I think by default, I have it compiled with the memory fault, memory manage fault. And that is basically an MPU violation fault. So let me start the debug. And here we have a system. This is our Kyle MDK environment for embedded code, and I use a U-Link Pro with a trace capability to get some additional information on the exceptions. But again, it's not mandatory to use this sort of debugger, or it can be a very simple one, or just a standard output as well. And we have this system analyzer that shows graphically a bit information on what really happens in the system. And here is a event recorder. These are the events that we annotate the RTOS, for example. We see all these thread switches, and you can configure it. I think it's hundreds and hundreds of different events that we can capture. And so here we have a list of threads. And this is I don't know if it's maybe too small to read, but we have two threads from the user side, normal and safe mode operation, and they're just getting regularly ticked. There is nothing else really happening there that much. But at some point, I can trigger this fault that I have configured, and I press a button, and I stop just to avoid too much stuff in there. So the trace capability allows us to see the interrupts right there. And you can see there is a memory management interrupt. This is basically the memory management fault that I triggered. And we can go and see a bit more. It's a 54-second, a bit more in the event recorder, what happened. And here we have this registered a bit more information from that interrupt and stored it into this uninitialized RAM. So then we resetted the device, and again we indicate that there was a memory management fault registered before reset, and we also can have direct access to all that information, to the fault registers. And that's where it gets cryptic, of course, and you need to open technical reference a bit more. We don't save that effort currently. But you have all that information, and as I said, it can be logged in your CI as well, so it doesn't get escaped. And if we check the thread operation after reset, we basically just continued serving both threads, right? So this is sort of, it's not a real recovery, but it's just to indicate how this CMSIS-View works. In the proper system, you would transition to some fail-safe state that ensures that there is no harm possible. But we can do it a bit differently. We can now change to the same fault, but triggered from the non-safety thread. So this one we did reset because it came from an unknown source, or from an interrupt. I think we do it. So we couldn't try any recovery, but we can trigger it from a non-safety thread, and then see how that gets handled a bit differently. So I'll start it and then reorder it next to each other. So both threads are serviced regularly, and then we trigger a fault, and then I stop. Let's see. Yes, so here we had again the memory management fault, and yes, so if we go and analyze those registers, there we would see this information that it came from a thread, and then we trace back what thread was it. And here we don't do the reset. So we don't do the reset. You could also see that from the flows here, and we just suspend the non-critical thread, right? And we can see it also from here. It stopped being served. We only have a safety thread running, but in that sense, we have protected our safe operation from non-critical function. Okay, so that was a brief demonstration. If any questions, you can always come. The example that I used is with FuSA RTS, but it's actually as I mentioned, we bring this functionality into the standard CMSIS as well, and we will make the example public somewhere on the GitHub that will not require any FuSA RTS specific package, but will run on the standard CMSIS too. So just to, if you don't need it specifically for safety, but general embedded implementation, that can be used as well. So to summarize, we have we have looked into how Arm Cortex-M IP is prepared for safety, right? So we do care for that part in our designs. We also have FuSA runtime system that implements process isolation and allows you to build mixed criticality systems. I didn't mention that, but we also have a compiler toolchain that is qualified for a safety project. We've seen a demo of CMSIS-View and the process isolation working in action. And large help for developing and debugging all sorts of this project is our ARM development tools, Skull, MDK, Ulink Pro, that we also actually use for our system, right? To certify our FuSA RTS, we only use ARM tools for development, testing, code coverage, and so on. We use some other tools for requirements or analysis, but there is we prove ourselves that with our tools we can achieve all the necessary certifications as well. And ARM is generally committed to functional safety. It is driven by our focus on the automotive in first place. Not only Cortex-M, it's actually mostly non-Cortex-M in the automotive. But we add Cortex-M2. We provide a broad functional safety IP. We have certified software components by ourselves and the software tools. And we work with partners to enable them on that. And we have all the comprehensive documentation and certificates that prove that we are doing it correctly. So that's the end of my presentation.